Hi, this is the project demo for Team Space Invaders, consisting of Zach Elms, Benjamin Leidenselers, Nicole Miller, and myself, Allie Rose. Our project was to build an emulator and run Space Invaders. So what is emulation? Emulation aims at replicating the functionality of a piece of hardware, allowing programs written for a specific environment to run on other platforms. In our case, we built an emulator of the Intel 8080, a microprocessor released in 1974. Emulation is unique in that it replicates hardware functionality and doesn't change the original software. In that way, it preserves the original format of a vintage piece of software while making it accessible on modern platforms. We're going to showcase the abilities of our emulator by running the original ROM file of Space Invaders, which was originally released in 1978. We're going to start by walking you through our development process before showing you the highlights of the final project. So I'm going to throw it over to Benjamin to talk about our environment setup.
Hi, my name is Benjamin Leidenselers, and I'm presenting the project environment slides here. So for a programming language, we used C, which has a long history of success in lower level programming. And we chose this because it has a lot of learning resources, mature tools, and libraries for a specific project. Plus, it's been a great learning opportunity. For writing code, we used Visual Studio, which worked great because Windows was a common ground for us. And Visual Studio has a lot of mature tools like debuggers, memory inspection, things like that. And it allowed us to use CMake to describe the compilation, which was really helpful, especially when setting up the testing pipeline. We wrote a lot of unit tests. We used the Unity testing C library, and this integrated really nicely with CMake, as well as Git and GitHub, which we used for development. And that allowed us to make pull requests and manage parallel development work, and also run things like GitHub Actions and a project board to make sure all of our code would build cleanly and pass all our tests moving on. And we also used SDL3, which was a major library that allowed us to do visual work. This also handled things like input and also has modules to handle sound and a lot of other things. This was really helpful, and you'll hear a lot more from that by Zach later. So next I'm going to introduce some of the specific works I did. I did a lot of work on build stuff, environment stuff. You can see here I set up the initial repository. I set up all the compilation rules with CMake, project configuration, including formatting for Visual Studio, the unit testing framework, and the GitHub action that I mentioned earlier. I tested 3 instruction groups. I tested the call group, the register pair group, and the direct addressing groups, which were really helpful for debugging later. I also worked on some good functionality. I had a disassembler proof of concept early on, and I helped Zach with some of the SDL tasks, so I had some flexible window scaling and resizing. And finally, I did a lot of debugging at the end to sort of get the game working and fixed a lot of crucial bugs and learned a lot about the emulator and the instructions that I hadn't learned already, which is a real joy. Okay, thanks. On to the next person.
Hi, this is Allie again. So let's talk about the disassembler. The projects that will be running on the emulator are in machine code. So the job of the disassembler is to translate that machine code into something more human readable, essentially undoing the work of an assembler. In our case, we built an opcode struct to hold all relevant information about an instruction. This made it easier for the emulator to handle a variety of instructions and helped with debugging later in the project. While the Intel 8080 has 74 distinct instructions, a single instruction might have multiple variations, as we see in this code snippet from the disassembler. Here, there are 4 hex values that all indicate an INX operation on a different register. So the opcode struct will hold an assembly language name for the operation. It'll hold the number of parameters and the number of clock cycles that the operation should take, which helped us with matching the timing of our emulator to the original Intel 8080. It also holds the kind of parameter, either a register, 8-bit or 16-bit value, and then the actual value for the parameter. Here's the work I contributed on the project, mostly in chronological order. Benjamin set up an initial structure for the disassembler, and I worked to implement all instruction translations. I also wrote tests to verify the opcode structs were properly filled out. I implemented 2 sets of instructions for the emulator, the accumulator arithmetic and accumulator rotation instructions. In PR28, I also wrote tests for these instructions. I contributed some other minor adjustments to the emulator and wrote tests for a couple other instruction sets, the data transfer and immediate instructions. Lastly, I implemented a terminal-based start menu to allow the user to choose from the ROMs listed in a directory of our project. Like the rest of the project, I worked in the C programming language in Visual Studio and used Git/GitHub for version control. I used Unity testing for all test modules. I also used the windows.h file for the start menu to enable the program to list the contents of our ROM directory on Windows-based systems. This mostly followed our original plan. The only deviation was with the start menu. Originally, we planned to implement a graphical start menu. Once I learned more about SDL, I determined this wasn't feasible in our time frame using SDL. Instead of importing another library, our team decided we should pivot to a simpler start menu to achieve similar functionality as we originally planned. One challenge was ensuring that the disassembler would pass the expected information to the emulator, and this required really good communication with Zach, who was implementing our main loop, and Nicole, who was setting up the structure for the emulator. Debugging at the end of our project was also a challenge, as there are thousands of instructions the emulator will run through in a single second, so pinpointing where our issue was at was really tricky. Communicating with the team where we were seeing potential bugs and sharing techniques for debugging was really helpful for me to help isolate the areas of code to check out. I learned a ton on this project, from getting comfortable programming in C, to learning about emulation, to coordinating as a team to break up a large project, tackle separate sections, and stick them back together to create something really cool. I'll throw it over to Nicole to talk about the emulator.
Hi, my name is Nicole Miller, and my part of the project was writing the code for the emulator and the code for the memory and for tracking the CPU state. The steps I took in development began with reading these manuals here, the Intel 8080 Microcomputer Systems User's Manual, the Intel 8080 Assembly Language Programming Manual, and the 8080-8085 Assembly Language Programming Manual. I then created a spreadsheet with all the opcodes and mapped them to their assembly language instructions. Each instruction was categorized by an instruction group. Here's a screenshot of some of those information that I have on this spreadsheet. The instruction groups were used to divide the instructions into separate files for the emulator, which were grouped into a folder called emulator, which is seen here on the left side. The code in the emulator folder is responsible for simulating the behavior of the Intel 8080 microprocessor by executing various types of instructions. Each file in the folder handles a specific category of instructions, and the main emulator loop in emulator.c, and here is the main function here on the right side. It calls the appropriate functions to execute for the instructions based on the decoded opcodes. The emulator manages the CPU state, including the registers and the status flags, and simulates the execution of instructions as they would occur on the actual hardware. This is a list of the pull requests that I worked on, and they can be seen on GitHub. Technologies I used for my part of the project were Git, GitHub, the C programming language, Visual Studio, and the Unity testing framework for unit testing. We use these technologies because as a group we wanted to standardize the technologies we used, and these were the ones that we decided would work best for the project. Working on the emulator was mostly straightforward, and the end result followed the original plan really well. I can't think of any deviations that I took. The main challenges I faced including the timing because the rest of the project relied on the emulator code. Another challenge I faced was that the Intel 8080 Assembly Language Programming Manual had some confusing, which later turned out to be incorrect information. Fortunately, I was able to use the other resource, the 8080-885 manual, and that had more clear and accurate information. The main thing I learned from this process is that when faced with a large project such as this and with a short time frame for completion, it's good to be able to divide the work between other people and have a group that is working on it. There is no way I would have been able to complete this project by myself given the time constraint. Thank you.
Hi, I'm Zach, and I was mostly responsible for the main loop, and that was made using C and CMake, but I interfaced mostly with SDL, which stands for Simple Direct Media Layer, which basically handles displaying to the screen and keyboard input. So in the main program loop, It's pretty easy. You basically load the ROM, and then you send that to the disassembler, and then you send the return of the disassembler to the emulator. And then in terms of SDL, it's just about getting the window up and then displaying something to it. And then I was responsible for splitting that up into different files to make it easier to use. For user input, the Intel 8080 has in and out opcodes, which basically interface with joysticks, coin slots, and a shift register, which I'll talk more about in a moment. So here's a basic development plan on the left, what was originally going to happen, and then on the right is what happened, with two main differences. I pushed the in and out opcodes until later, just because I was already doing SDL stuff, I thought I'd keep it together. And then the in and out opcodes ended up taking longer than expected to implement and test, so I didn't have time to add in sound. And that was one of the challenges I faced, was getting in and out implemented and tested quickly, and that didn't quite work out. And what I realized from that is that in previous sprints where I'd finished something, I should have just started on the next bullet point instead of waiting until the next sprint, because then I could have started the in and out opcode sooner and thus finished them sooner. Here's the main file of the program, basically initializing stuff, displaying it, and then destroying it. So we'll look at initializing. Most of this was me with some help from Benjamin. We're basically initializing all the SDL stuff, all the game stuff, and then here we're cleaning it all up. So here's our actual loop. Below this is a lot of Benjamin's code, and then some of mine was the foundation of that. But I was wholly responsible for the update function, which basically detects user input, and then here we actually process and set the necessary ports. And so I'll talk about those in and out opcodes. Basically, the in and out opcodes would end up calling these functions where the emulator would read in from different read ports and could write out to different write ports. So you'll notice in here we're setting the value of different read ports to different values, and then the emulator will read them in here, and here are where those ports are defined. And now the shift register I mentioned before is implemented with in and out codes as well. Basically, the emulator sends data out to the shift register. It can set the offset of the shift register, and then here's the code for actually shifting the bits. So now let's actually see it play. Here is our main menu. You can see Space Invaders is loaded here, but we can actually dynamically add other ROMs. You can see now I've added the ROM for Call of Duty Black Ops 6, which I've diligently ported over to the Intel 8080, but we'll start with Space Invaders. Now the game is running. You can see our controls got printed out over here on the console, and this is what you'd see in arcade in its subtract mode. So we can go ahead and press C to add coins. So there's a one-player mode and then a two-player mode. We'll start in one-player mode. And here we go, playing the game. So I can shoot, I can move left and right, I can dodge, I can destroy. So we'll go ahead and we'll end this game real quick so we can go to two-player mode. So the game successfully finished, depending on your version of success. So add 2 credits to do two-player mode. And what will happen is player 1 will go until they get hit, and see how high of a score they can get, and then player 2 will go until they get hit. So if we go ahead and just get hit here, my score is an astounding 0, and then we go to player 2. And here we have player 2. And it goes until player 2 gets hit, and then it'll go back to player 1 until we're out of spaceships. So in terms of further development, it's just expanding on basically what we already have. So that'd be adding in sound, and then allowing the use of other Intel 8080 ROMs that are not just Space Invaders. In terms of commercially selling this, that probably won't happen, just since we're using open source libraries. And then Intel or Space Invaders is not our property, so we can't sell that. And this is a meme that we included at the end of our project plan, saying that we will build an 8080 emulator. I thought it was only fair to now change it to say we did build an 8080 emulator and we did on Space Invaders.